So first of all, I have passed out from NSS, the College of Engineering. I'm very proud about that. I was the second batch, from the second batch of instrumentation and control systems. I passed out in 1986. And one thing, I was fortunate to be in the instrumentation and industrial automation systems throughout, from 86 to till now, that is all throughout the 34 years. So very briefly touching upon my journey of 34 years. So starting with the job at Instrumentation Limited, Kota, as the DCS application engineer. So in 1986, that was the time this microprocessor based. We cannot even say computer based. Probably it is a time only PCs and all not really established. Internet is nowhere in this kind of even in the imagination at that point of time. So, but then microprocessor based controllers were coming into the picture. And 86, 87, that period, maybe 86 to 90 was a period, this kind of distributed microprocessor-based control systems were coming to Indian market. And mainly the rich oil companies were trying to get that. Those were the first installations. And I was part of the Instrumentation Limited team, which was implementing that. And I had the opportunity to kind of build the complete control logic requirement for various plants, mainly refineries. So you can guess that at that point, this is totally new thing, and the entire organization in Instrumentation Limited, very experienced people on industrial automation, but then they're all experienced on the analog systems. So those who came from college, just like me, few people were kind of, the entire responsibility was with us, and we had to kind of understand and build the system and implement it in the refineries. So it was, I just mentioned that only because of one important point, that whatever fundamentals I learned from the college days, especially on the PID and various different Boolean logics and analog controls and all, those were kind of immediately after starting my career, it was very useful. And I was just kind of trying it out, right, from whatever learned from college, and the new system is in front of me, and implement that, and nobody is there to gauge, because it is the digital new thing coming up. So the organization is depending on the newcomers. So that was the case. That was very good experience. So implementing those kind of systems, that was mainly from Toshiba Digital Distributed Control Systems. And then after 5 years of that experience, I moved on to CDAC Trivandrum. There I was the deputy director, and in fact, I started as senior engineer, then became deputy director, and mainly was managing the software and hardware teams to build the similar kind of systems, which I have seen in the previous 5 years during the experience with Instrumentation Limited. So that was again very interesting, that I know what happens with in the field and what is the expectation of running plant, and then leading the software and electronics hardware team to, or rather embedded systems team, to build the hardware and software to realize first generation indigenized computerized control systems. And that was till 2000. And then moving on to Nest Software, that's a private company based out of Technopark. And this was more again after say 14 years of experience, I have become kind of a program manager, senior management level, and then heading the kind of entire business of industrial automation for Nest Software. And that was again another 14 years. So I built the business of industrial automation of Nest from kind of scratch to something like 4 to 5 million, winning many big logos from US and Europe. And finally, this company, Nest Software, was acquired by Quest Global. So I have become part of Quest Global from 2015 onwards. And then I continue with that. I'm the COE leader. Basically, I'm playing the role of consultant to the software and the hardware development teams. They support the major OEMs, that is original equipment manufacturers in the field of industrial automation. That is my current role. So I give guidance, I make them build the capabilities related to what could be required by these kind of OEMs and all that. Okay, moving on to just very brief about Quest. Quest is a engineering, pure play engineering company. That means I just want to bring the difference that you hear a lot about IT companies like Infosys, Wipro, HCL. There are many big companies. But all of them are into everything, like say banking, finance, enterprise systems. Those are all big business. But unlike those companies, Quest is very focused on engineering services. We do only engineering. So we have around 13,000 employees. In that, you can say 95% is engineers, either mechanical, electrical, instrumentation, computer science engineers. Engineers makes around 12,500. And so it's a pure play engineering company. And all that we learn from college and all those things are kind of put into use, and a lot of value engineers add here for our customers. And this is a truly global company in the sense that we have 15, we operate in 15 countries and 67 delivery centers we operate in. 67 delivery centers means 9 of this 67 is in India. Rest are all in US and Europe and Japan and Singapore and Philippines and all that. So it is and half of the employees are actually foreign nationals. So the culture wise, the teaming wise, it is truly global. Every project, everything happens with many people joining from US, Europe, Japan and India and all that. It goes like that. So it is not just engineering and just a company. More than that, we have a global culture in that. It's a very kind of multinational global environment where engineers can work and add value. Okay, so at the bottom you see the domains we are operating in. Just give me a minute. Yeah, domains we are operating in: automotive, oil and gas, power and industrial, rail, aerospace, aero engines, high tech, and medical devices. And we partner with our customers. So we don't have too many customers. Unlike many other IT companies, we don't have hundreds of customers. Maybe we have 20 customers and very focused, and maybe 500 or 800 or 1,000 engineers work only for that customer. That kind of a deep relationship we have with the customers. Okay, this is the last slide on the company information. I will quickly move to the topic. So here just I want to bring your attention only to one point, which is at the center. We operate in energy and industrial. You can see the client base, like the big names there, the Fortune 100 companies in energy and industrial, like ABB, Schneider, Siemens, Toshiba, Mitsubishi, Hitachi. All of them are our customers. And all these activities, what we do in oil and gas, power and industrial, is either industrial automation or adjacent to industrial automation. So plant related engineering activities and all that. Industrial automation, basically, if you look at from the industry's application point of view, it is basically in two streams, two packets. One is process control, and another one is manufacturing automation, or we can call it as factory automation. So process control, these things probably you know all these things, but I'm just bringing it up to bring all of us on same page with respect to some of the terminologies and the basic understanding of the industry. So process control is basically the regulating process industries like power plants, refineries, petrochemicals, fertilizers, paper and pulp, water treatment plants, cement plants, etc. Mainly this, the key parameters, there are flow, pressure, temperature, level, and all that. These are very slowly varying signals. So you only need to, or scanning it and reading it in every 1 second is kind of good enough for managing those kind of plants. But the challenge remains on the regulating control activity, where you bring in your PID control, which is the kind of central piece of this kind of control. I mean, the process control part, and then cascading them master slave PID configurations, and like thousands of such control loops coming in a power plant and refineries and all. And that makes, and their kind of interplay or interactions makes it kind of extremely complex. And the redundancy and safety and all that aspect is also very important. So here RTU is one of the keyword remote terminal units, which is the electronics or the hardware piece which collects data from the sensors and then do the processing and control logic implementation and all that. We will see it in a structured form in another slide. And then that RTU or PAC, Programmable Automation Controller, that is another term used for that. So RTUs and PACs are basically designed to handle this kind of slow varying signals in normal case. So they are built for process control. So they are more predominant, these words RTUs and PACs are more used in the context of process control. And the complete system with the operator consoles, the RTUs, PACs, all that comes together, and that is the distributed control system. Again, DCS is also more commonly used in process control, not in the other stream, in the manufacturing automation. I'm just trying to differentiate both. And SCADA is, of course, used in both sides. SCADA is more kind of software which can get connected with any hardware to acquire data and help the operator monitor and control the plant or whatever asset asset being monitored. Then there are another difference is the programming, the way users build the logic into the distributed control systems for process control is using FBD, that is functional block diagram programming, or structured test programming, or sequential flow charting programming. So these are again all these things: FBD, ST, SFC, DCS, RTU, PAC, regulating control, PID controls. All those things are very much related to process control. But when it comes to manufacturing automation, the scenario is a little different. Even though fundamentally it is all doing the same thing, capturing the information, processing it, and doing it for the control decision making, and presenting it to the user, the operators. But then fundamentally, in the manufacturing automation, there are many differences. Like instead of the analog varying, slow varying parameters, there will be a lot of fast varying, mostly discrete signals, digital signals coming from relays, switches, interacting with the robots, many different drives to be controlled. So the PLC is the thing which is used there. PLC is similar to RTU, but it is mostly used for this kind of digital or discrete manufacturing industries. Example is like aircraft manufacturing, automotive manufacturing, semiconductor factories, that means chip manufacturing factories, mobile factories, etc. These are all batch by batch, discrete control, mostly digital. Digital means discrete on-off controls, but very complex logics, interlocks, and needs to be there to have the control. And equipment control, specifically like DCS in process control, equipment control is very important here in the manufacturing automation side, which we will see a little bit more details in another slide. So here the scanning has to be very high speed, and high accuracy requirements are all there. So traditionally, these are two streams. PLCs and RTUs are designed for different purpose originally, but then later on, as technology picked up and a lot of advancement happened in the technology, PLCs started kind of claiming that all that RTU is doing can be done by PLCs. Similarly, RTUs are capable of doing all that PLC is doing. So the gap is kind of very narrow now, or more or less same. Any device you can take, and they are both of them are offering a very high degree of flexibility. So a PLC can be brought, and you can put some boards which do the exact activities similar to RTU and all that, the vice versa. All that is possible either way. It is kind of converging to one kind of hardware, one kind of software, and all that. And one point I just left here is that again, on the discrete manufacturing side, we do the programming not by function block diagram and all that. The ladder logic programming is very popular here. That is being used for this kind of scenarios. Okay, then having a quick look at the DCS, the process control scenario, what hardware and software goes into that? Okay, at the bottom, the RTU electronics, as we mentioned, that will have some CPU modules and various communication controller cards, different IO boards like analog inputs, analog output, digital input, digital output, pulse input, those kind of different boards to take the right inputs from the field. And all these things are managed by the dedicated power supply, the communication through some backline and all that. So it is a kind of dedicated hardware. I'm not sure whether we have RTUs in our lab. I'm sure there may be PLCs, but both are theoretically both are same, but functionally it is used in different contexts. Someone wanted to say something? Okay, I'm moving ahead. Okay, similarly at the DCS and SCADA function, core functions, I'm not elaborating on those things in the interest of time, but there are various important functions like the first and foremost is implementing the logics related to alarms and events and all that, and having the trends and HMI and the complete management of the whole operator console and engineering functions and what should go to the RTU, what should get downloaded to the RTU for implementing in the field. All those things are decided by various tools and systems within the DCS and SCADA core functionalities. And finally, it is all to be presented to the operator through HMI packages. And there are various ways like HMIs or reports and real-time trends, historical trends, and all that, by which operator will have a view of the whole plant. And then you need to have the engineering functions as shown here. Engineering functions is kind of offline tools. Offline tools, I mean to say, in normal running plant, you have RTUs running, you have all core functions of SCADA, you have the operator monitoring the whole thing. But then these are kind of offline tools. Normally it is called builders, logic builders, HMI builders, report builder, log builder, etc. Using that, engineers program the system to get the desired functionalities implemented and downloaded to the RTU and whatever needed screens built for the operator, etc. And then another point is about the kind of connecting it. In every case, when this kind of DCS is implemented, there will be a lot of requirements for connecting it with the third-party systems. So the system needs to have some standard interfaces like OPC, Modbus, Profibus, Profinet, IEC 61850 compatibility and all that. So we will have a closer look at that separately. And then finally, of late, there is also requirements to monitor the data over the web. So there are some interfaces, adapters built on top of DCS to monitor them over the web. And these are all related to the product usage or product development. If you ask where the real hardware or embedded system development or the software development comes in, all those things comes in this kind of a product development where the OEMs like say Schneider, ABB, Hitachi, Toshiba and all that, they make this kind of systems. So they need a lot of that kind of software and hardware development skills to build that. And in a way, companies like us, Quest Global kind of services companies actually provide those kind of services. So these big OEMs like Toshiba and Hitachi and all, they come to us for taking that services to build this kind of product. And then once this product is made, there is also still a lot of need for kind of implementing that in the field, like understanding the field requirement, and then based on that, configuring the whole DCS and commissioning it. That's another big stream of activity. And one thing which is mentioned here, one is beyond that is the operation and maintenance. Say first one is the product development. That is a major portion we said. And then implementing that product in the field, that is deployment. And then once it is deployed, the operation and maintenance of the system as well as the asset, that could be a plant or equipment or whatever, that also needs to be done. So engineering services are needed in all these segments. Okay, this was a little bit in depth on the process control part. Similarly, on the manufacturing automation, I will explain with one case here. What you see on the left side is a semiconductor manufacturing fab. It's a clean room. It's a dust-proof clean room where see these are all equipments. One semiconductor manufacturing equipment is something like what you see on the right side. And in a modern fab, there will be something like 300 to 400 such equipments, which will be processing the wafer to find and producing the final chips. So actually, this wafer will go through various such hundreds of such equipments, like as I mentioned, 300 to 400 equipments. Each equipment will be doing some kind of inspection, some kind of processing on the wafer, some kind of measuring and all that. So it is discrete, like one by one. Each wafer will be stacked in a cassette module, like what is shown at the center, and this will be moved from equipment to equipment through this entire fab production line. And the movement and the kind of processing or the measurement of the wafer, all those things are kind of done automatically. The entire thing is a clean room, so the whole thing has to happen mostly automatically. Very rarely human intervention will be there. So that is where the manufacturing automation or equipment automation comes in. It's very kind of complex. Just an example, this kind of one equipment itself will have this kind of a cluster tool, which is shown in the middle. So cluster tool is nothing but which is a complex mechanism which handles the wafer, taking from the cassette module and putting it in some chamber and process it, heat it, or do some processing on that and take it out. So putting that and taking it out and all that is done by different robots, like atmospheric robot and vacuum robots which operate in the vacuum and all that. So this kind of complex equipments needs to be automated by equipment control, and then hundreds of such equipments needs to work together, and the material needs to move within the equipment and between the equipments smoothly with minimal or no manual intervention. So that is a challenge there. So it has to be very, very accurate and high speed scanning and high amount of data handling and all needed. So this is just an example of manufacturing automation scenario. So this, whatever I mentioned, is shown here on the left side, is the typical scenario which you are all familiar from the plant, then the different transmitters and final control elements and all that, and the electronics, the RTU PLC stuff, and then the operator consoles, and then the supervisory console and all that. Typically in the industry, this is discussed in layers, like layer 0 is the real plant, layer 1 is the field instrumentation, layer 2 is the data acquisition and control hardware like PLC, RTU and all that. Layer 3 is the control part, like DCS, SCADA, energy management systems, distribution management systems, etc., etc. And then above that, it is up to this, the green portion is the one which really does the monitoring and control of the asset. I use the asset common word because it could be a plant, it could be an equipment, it could be a manufacturing line or anything. So it is done by this green portion, layer 1, 2, 3. It is also known as the operation technology layer. OT layer is the very commonly used term in industries. And above that, we have layer 4 and 5. That is basically the planning and scheduling, like advanced process control, load sharing, the work planning, workflow planning, scheduling, workforce management systems, all those things come, and say MES, manufacturing execution systems, all those things comes in the layer 4. And layer 5 is purely IT. IT means the enterprise systems, like the supply chain management, enterprise resource planning, customer relationship management, geographic information system to monitor geographically spread plans and assets and all that. So again, this 4 and 5, this layer is known as the IT layer. So traditionally, this IT layer, this is huge amount of software, and it is domain independent. but the layer 1, 2, 3, the OT is very specific to the plant. Say the OT layer for a power plant and OT layer for a refinery is different. OT layer for a manufacturing industry is again different. So it is very much related to the domain. So the OT layer is highly coupled with the domain, and the IT layer is kind of generic software or management software kind of thing. So, but the challenge today is kind of integration of that. So these are all the kind of existing stuff I discussed so far, and now I'm jumping to what is coming up. So this IT OT integration is one of the major theme coming in. Seamless data exchange. Actually, integrating and getting the right data from OT layer to IT layer is a challenge today. People say there are interfaces, you can easily get seamless data transfer and all that, but in reality it's not that easy. It is product to product, scenario to scenario, it is different. So a lot of domain knowledge needed there, a lot of IT knowledge needed there. So it is a challenge. So IT OT integration, tight coupling of these two things is a trend happening there in the industry. So IT OT is again driven mostly by various industry standard protocols. So what is that? The core of IT OT integration capability, if you ask, that is actually the knowledge of related protocols, many IEC protocols. Okay. And then the next one is the next generation control system. This is very interesting. This is actually a disruption happening in the field of the process control. The whole OT system and the IT system, the entire scenario is going to be changed. It is because of the entry of cloud native technologies and various new advancements in the scenario. The old kind of structure, what we have discussed so far, the RTUs, PLCs, and all those things are going to be kind of changed, disrupted. We will have a look at that also. And then finally, the third trend is the digital tech stack application. Like as you who might be very well aware of many of those things, artificial intelligence, big data, AR, VR, blockchain, industrial IoT, and with the 5G, it is even more important, and edge analytics. Those kind of things are coming in, and that is making the change. That is the advanced use cases, not just capturing the data, doing the control action, and then doing some minimal analysis. It is going much, much beyond that. The whole thing can be modeled and analyzed, and a lot of insights can be found, and accordingly better control, better prediction, better asset management can be done. All those things are enabled by the digital tech stack. So just to summarize the three important trends coming in the industrial control scenario. First one is IT/OT integration. Second one is the new generation control systems. I think it may not be very clear to you. I will explain that. And then the third one, it is the digital tech stack application, which is changing the kind of use case scenarios drastically. Okay, jumping to all three, each one of them to have a little bit more details. So this is about the IT/OT integration, the first trend I said. There is nothing much here. I'm just listing some of the very important protocols which is needed to integrate the OT systems with the IT systems. So these things you may be familiar, like Modbus, Ethernet IP, DeviceNet, HARP, and all these protocols are very popular, traditionally being used. But then it continues to be in the market, in the industry, very widely used even today. And I'm not sure about OPC. This needs very special attention from whoever want to get into the industrial control system segment. So OPC is OLE for process control. It's an open standard by which any system can be said open. Means if a company, like say I'm just picking a name, ABB making a DCS, and they are saying that my system is with the OPC interface. That means he's saying that his system is open. Anybody can fetch data and give data back to his system without getting into the internal details of the system. So OPC is a generic interface. So this was there in the field for last 20 years or even more. and it has been developing in line with the trends in the market. And what OPC DA, OPC A&D, OPC XML DA, all those things are actually legacy, old stuff. And what is in the market today, whole thing is OPC UA, that is as per an IEC standard. That is very important. It is widely being used. Everybody is implementing. Most of the people has been implemented already. And what is coming up is OPC UA publish subscribe model. So OPC UA, the first one, IEC 62541, is basically the client server model. That is now coming with a publish subscribe model and some time sensitive network and all that. So if somebody wants to look at what the next protocol I need to focus and work on, I would recommend that we go for a study and make a deep dive on what OPC UA publish subscriber model. There are a lot of free open source code available. You can get that, and you can build on top, you can study and then build on top of that. Okay, then so those kind of interfaces are required to really realize systems communicate each other, and specifically IT/OT integration communication. And then cybersecurity is another important theme. There is also some IEC standards. So most of these protocols are with the related IEC standards. Substation automation is driven by some digital substation IEC standards. So the summary is that we need to kind of look at these protocols, especially those marked ones like OPC UA PubSub, or maybe the IEC 62351 cybersecurity, and take a deep dive, understand, and try to build on that. So this is all services companies like Questian and all doing, but the new protocols are just now only kind of even we started doing, but the academy is doing that. The colleges doing that will definitely kind of will be very useful for the students that are coming out of the college, as well as for the industries. So I have also listed some of the other standards. I will share the slide for the benefit of everyone, so you can look at these standards and pick some of those things which is closer to your area of activities. And this is the next trend. I need to spend 5 minutes here. This is very, very important, and it is also equally exciting that to put it, the problem statement at a very high level, actually the plans are built to last for, say, for example, 100 years or even more. A refinery or a thermal power station or a factory and all that. And unfortunately, the control systems are built to last only to 10 to 15 years. Within 10 to 15 years, the electronics goes obsolescence. Nobody will be supporting that electronics. The components are no more available. It needs to be replaced. So for all these refineries and all these plants where they have gone for this, is faced with a big challenge all these years. Last 40 years, they have been, every 10 years, they go for changing the new system. When they change with a new system, even bigger hurdles, like the entire programming done on the old system needs to be ported to the new system. Or they have to go for upgrading with the existing supplier. That is another challenge. Like existing supplier may have some bottlenecks, some performance issues and all that. Now they are unable to get rid of that if they go for upgradation. And if they change entirely with a new system, new make, then the entire program, entire logic, HMI, reports, all that is programmed into that has to be reprogrammed. Huge amount of effort. And this is a big challenge. And apart from the other challenges of no way to get the data out of these kind of systems, no way they are able to use multiple systems, I mean to say multi-vendor systems, like one RTU from ABB, another RTU from Schneider. It is impossible at the moment. If you somehow connect it, it will affect the performance. So those are some of the challenges with the current ICS scenarios. So I just mentioned that you cannot mix subsystems. That is, you cannot have multi-vendor. It is not really open. All these systems are basically proprietary, even though they say that it is open. So most of the existing systems does not really support the digital tech stack, like the artificial intelligence and IoT and all that stuff. And the users cannot be away from all that, because that brings a huge benefit. So it's a big dilemma now, how to replace this. If we replace it, it is going to be very costly, and the new generation systems also not fully emerged. So a lot of confusion is there. So, but this is the time it is emerging. So the whole thing I just mentioned to bring to the point that this is leading to some of the important technology elements, which is something which, if we focus, it is the future. Okay, the key solutions, as I mentioned, addressing all those challenges which I mentioned, making the system open, plug and play, agile. Due to lack of time, I'm just rushing through. So, the system today, the systems are made functionally safe and secure by adding components to it. But the new generation system has to be by default, by design, by plan. It has to meet the intrinsic safety and security, and it has to be with the digital compatibility. So this column, technology element, is important one. Here, as I mentioned, some of the important topics, OPC UA PubSub is definitely an important topic. Then virtualization. Virtualization means, again, the hardware and software, the firmware, that means the embedded piece as well as the application software, both needs to be kind of supporting virtualization. That means making it independent of hardware and the software. So, for example, today I'm running a particular logic for controlling my boiler here, and that logic is packaged in such a way that tomorrow I go and buy another hardware, another RTU there, I should be able to port this logic which is already built into the new hardware, which is a new hardware base, which is with a new OS, but my functionality, which is already built and packaged, is independent of hardware and independent of OS. So that can be achieved by virtualization. So then software modularization, as I said, packaging it, I just use the word packaging, like the functionality can be packaged to run any hardware. So that packaging is, again, the containerization and its dynamic deployment and all that, which is the new technology in the cloud native technology spectrum. And then, of course, a lot of modern hardware design is also coming in there, and various IEC standards for functionality, and all these points, digital tech stack, I covered. So these are some new technology elements which goes into the next generation industrial control system, which is now shaping up. And this is being driven by a forum called OPAF, Open Process Automation Forum. This is funded by the giants like ExxonMobil, and a lot of the very big companies are funding and participating in that, because they are all stuck with this scenario, like changing every 10 years, changing the hardware, and if change is needed, it is too costly. So they are trying to address that. And NAMUR is another similar kind of forum. They are also driving towards that. And OPC Foundation is the one, they are making the OPC standards, and OPC UA is the latest. OPC UA PubSub is the latest. Okay, so these are something you can explore on Open Process Automation Forum and all, what they are doing, how colleges or universities can participate in that. There are already many. There are many services companies, many original equipment manufacturers and all that. And finally, this just 30 seconds on this. Essentially, the whole thing, what we have seen here is the field electronics or the edge electronics or the OT system or the IT system. All these things are basically microprocessors and the IT infrastructure. In a way, you can say this is simple IT infrastructure. In the enterprise level and all, IT infrastructure means it is just generic IT hardware. But here, in our process control scenario, it is all proprietary. But it is going to change. It is the entire process control system, industrial control system, is going to be with a generic hardware, which will be treated just like IT infrastructure, like some logic loaded onto the field electronic side, but due to some alarm condition or something, we are finding some performance issues. Some of that thing can automatically move to the edge electronics and run there. So the sharing of functionalities and the where it should run, when it should run, when it should move from this electronics to another electronics, I mean in IT infra to another IT infra, all those things are going to be dynamically controlled. So process control system is no more going to be a dedicated proprietary system. It is going to be just like any other IT infra. So that is the direction towards these companies are now moving. Okay, I'll not spend time here. This is, you can find all these things, OPAF I mentioned, OPAF reference design. Okay, OPAF reference design, this is in the OPAF website, and all, lot of material, lot of YouTube videos and all you can find. You can see all these yellow portion marked here is the new components. They have introduced a lot of new things like distributed control node, distributed control framework, distributed control platform, advanced this thing, on-premise OT data center. These are all new concepts. So they have brought in many of such things. So learning that and kind of trying out something. This is the right time to try out something because everybody is trying. Everybody is just trying to build. You can say there is no OPAF compliant full-fledged system as of today, but it sooner or later it will come. I think 1 week back the first mini system has been released by a US-based company, but a lot more to come. Okay, this is just for you to explore further. Okay, that up to that it is the new generation system, and this slide is just this is the digital tech stack usage in industrial control space is more generic. So considering again the time factor, I'm not going to explain this is this at a greater depth. Here very quickly, it is basically there will be IIoT platforms or IIoT framework, that is industrial Internet of Things. That is the backbone to capture the data at the edge or and then push to the cloud. And this kind of thing, which I'm sure that these are all very well known to you. This kind of things will ultimately get your entire data from the plant to the cloud. Once it is in the cloud, large amount of data can be analyzed, and quite a lot of artificial intelligence and all that can be done to realize many use cases which we have not even thought of. And some of them already in use is on the top, say remote monitoring and diagnostics, asset tracking and asset management using predictive maintenance, and digital field support means like using AR and VR. Like remote operation and management in the field. One field support personnel can look at the equipment or the device, and just by scanning it by his mobile or something, he can get the complete information at his fingertip, even with the guidance through augmented reality or virtual reality to help him. Like he does not have to go back and refer many files and discuss with many people to attend to the problem. It's all right there. It's all provided real time to him. So those kind of use cases. And there are a lot of, all these things also play an important role in physical security systems. So to make all these new use cases happen, we have to have a very strong data exchange mechanism as the backbone. That is where the IIoT comes in place in the industries. Okay, there are a lot of benefits related to that. There are some enablers, as I mentioned, AI, AR, VR, MR, edge analytics, and all that. In fact, this edge device, this will eventually replace our RTU and PLC and all that. Edge can work as a data concentrator. Edge can work as a, say, a gateway to pass data to the cloud, or it can even work as a RTU or PLC in future. So even looking at taking up a project where we make a small edge device, which partially do the function of a PLC and RTU, could be a very good project. Okay, this is just a repetition of the same 3-4 different use cases of digital and some of the technology elements you may look at, like for edge solutions, for digital platform solutions like Azure IoT Hub, AWS IoT, Predix from GE, Mindsphere from Siemens, like that, various platforms. So what is listed here in black is actually some of the established platforms. You pick that, understand that, and what Hadoop is doing, what Kafka is used for. You have developed some that kind of understanding that will be very helpful. Some of the popularly used technology topics or technology platforms or elements are mentioned here for your reference. So it is in all different layers, like web and mobile, another one set, and cloud native technologies, another set, like Dockerization, Kubernetes, and all very, very important. Any focus or any amount of effort you put on, say, doing something on Dockerization and Kubernetes will not go waste, because a lot of lot of drive towards that, building new microservices based systems. Okay, that's all. I think this is just for information, some of the popular use cases. And finally, coming to the last slide, these are the topics which I have already covered. 10 topics I recommend you to deep dive. It is big effort intensive deeping dive into all these. I'm just saying, I'm just showing the direction only. Maybe you can pick whatever relevant, whatever interesting, and then deep dive into that. And I can also help the team to kind of define the scope at a high level, if there is a team to kind of deep dive and understand that. So open system protocols, virtualization, functional safety, cyber security, edge computing, SCADA as SaaS system. SCADA is actually a package software sold today, but this can become a multi-tenant cloud-based kind of service-based system. SCADA as a service, it can go as a software as a service. So that's also a new emerging concept. We can think of building a POC for that. Digital twin is another one. Choose any factory device or a plant device and build that digital twin. In containerization, as I said, Kubernetes and Dockerization and all comes there, IIoT platforms. And finally, the full spectrum of cloud native technologies, all of them have an important role in next generation control systems. I think we have hardly, say, 7 minutes. So any questions, anything we can discuss?
Sir, in the process control DC subsystem, there was something called engineering functions.
Correct.
Can you please give a clarity on that?
Yeah, this is the one you are seeing, right? Engineering functions.
Exactly, sir.
Yeah, actually, as I mentioned, these RTUs and the electronics at the bottom, they do the real function, actually collecting the data, processing it, and implementing the control logic. And then based on the control logic, do the control action on the control valve or whatever final control element. So it is done by this, but it is defined by the kind of plant engineer who wants it to be done in a particular way. What is the computation? What is the logic? So there are some tools. Engineering functions means engineering tools. Say the first one, logic builder. Logic builder is a tool in which there will be a library of functions. He can drag and drop and build a function. And that function ultimately saying that, say, you take the data from, say, so-and-so channel of the so-and-so board, and then do PID action and give the output back to another board in another RTU, something like that. I'm just saying the example. So exactly what exactly the logic, that is the most important part. What exactly the logic to be done by these RTU electronics is decided by or programmed by the tool. This is in a way programming tool. It's not really coding. Coding also comes part of that, but generally it is function block diagram programming and all that. Using a library, you can build that. So building the logic, building the screens, building the reports, those are all the engineering functions.
Okay, sir. Sorry, so do you mean that is it a set of libraries so that we can drag and drop, like it's more like a template, right, sir?
Yeah, it's more like a template. It is like see the system. If we are buying from one company, say for example, ABB system we have bought, and ABB also provides these builders, the tools. So the system as it is, the complete the consoles and the RTUs and all is just arrived the plant, and now we have to connect all of them and use the tools provided by engineering function tools provided by ABB to build the required screens and required logic and everything. It is ultimately for the engineer or whoever doing the engineering function, for him to decide what this DCS should do. OEM gives only the standard things. Rest of the things has to be done. It is called application engineering. That is what I have shown here. So this is mostly I was talking about the software and hardware on left side. On right side, it is application engineering and commissioning support. This is actually the one engineer or a set of engineers. They use these engineering function tools. Tools means software tools to build the respective logic and the screens and all that and make it ready to run in the plant. Hope it is clear.
Yes, sir. Yes, sir. Thank you.
Okay. So building a logic builder and all, let's say, it is nothing new. It was there in the field for quite long. So I don't recommend you spend your focus and effort on that. But those are fundamentals. Understanding that is how the function block diagram programming, how that library, like it will be it will have an IDE kind of development environment where you will have all the functions. Say, for example, the square root extraction is a function. PID is another function. So you connect one input signal and select and drop the square root extraction function to do the compensation of flow signal, and then go and take the PID function from library and put it there on your IDE, and then connect the output of the square root extraction to the PID. Like that, you keep on building that. Actually, it's like programming. The real intelligence is being built by them. The system works based on that intelligence. And as I said, I specifically kind of underline the point that look at these IEC standards as well as the new trends as per the OPAF reference design. Those are some of the things which you can pick. You can study overall that what it is, where it is going, and why this is being done. If you have such an understanding, and then pick, and if you develop something like a DCN kind of thing, it will be very, very interesting for the industry. And if you build the OPC UA published subscriber, which I can say today, not many companies has figured out, or rather implemented that in a full-fledged way. But at the same time, if an institution coming up with a kind of pilot implementation of that, it's not rocket science. You don't need really big infrastructure also for that. It's pure software and a lot of things available in open source in the public domain. Anyone else?
So, good morning, sir.
Yeah, sure.
Okay, sir.
Go ahead.
Sir, in this same slide, you have discussed about the safety components.
Right.
Of can you please describe what are the components they have been using, or they are meant to use for safety?
Yeah, safety is basically the design. First of all, it is design aspect. Design aspect means if something fails, it should fail safely. Failure is possible. Any hardware or software can fail. But while designing a product or designing a system, you think of all that possible failures. And there is a very matured standard practice for that. Like what all the aspects you should look at while designing a product. These are two different scenarios. Safety aspects while designing a product and safety aspect while designing a system is two different things. System means you're putting many products together and building the system. So in both the case, what are all the different aspects one should look at to consider the minimal failure, and if failure is there, it should fail safely. I cannot get to the details on that because we have to take case by case. Okay, but otherwise, generally it is that you just, I will also take you to slide here. say functional safety, you look at the 61511, IEC 61511. This is a kind of a standard. Actually, 61580 is the mother standard of safety. From that, various standards derived for different streams or different areas. Like for aerospace, there is another standard. For industrial automation, it is IEC 61511. Look at that, that gives a lot of details. Just Google IEC 61511, that itself will give you a high level understanding. And if the college is having the IEC membership, if we do not have, I strongly recommend that we should take a IEC membership. And I think it is easy, or it is not costly also. It is for universities and all that. And then you can download this, and it's elaborate, like it's too exhaustive, but then you can pick some cases and study further on that. This is also another very good question, in the sense that the relevance of this is very, very high. In an industry like any process control industry, or companies like service providers or original equipment manufacturers like ABB and Schneider and all, if a candidate walking in and saying that I have a very good understanding of IEC 61511, I have done my project on that, it really carries a lot of weightage there.
Okay, sir. Okay, sir. Thanks a lot, sir.
Okay. I have no time limit. I can continue maybe if there are more questions.
Hello, good morning, sir.
Yeah, good morning. Go ahead.
Sir, I had a doubt regarding the IEC 61850 protocol. So
Okay.
you just included that under the subsystem automation system. So
Right.
why is it exclusively used under subsystem automation system? Because as far I know, like it can be used like in any systems for automations, like it works under the IED, like Intelligent Electronic Devices. So why can't it be used for the IT/OT operation systems, because like the integration?
This is that is a good question. Actually, IEC 61850 is specifically made for a substation scenario. It is, as you rightly said, it is for communication between the IEDs, intelligent electronic devices, as well as to the respective substation SCADA or substation automation system. So it handles very typical scenarios of that. And it is basically devices to the software communication. But here, the OT and IT communication layer is very different. There are two parts for answering this question. The first one is this 61850 is specifically made to handle substation automation scenarios, not a generic industrial protocol. All that aspects, the attributes, the devices, the model within that, all those things are for substation automation. That is why it is used only there. But OT-IT or IT-OT communication is basically both are huge amount of or a large scale software. Just to explain that, here I'm saying our IED and all those things comes here. IED to the layer 2 to layer 3 communication in a substation is handled by IEC 61850. But above that, the whole control system aspects end here at layer 3. From there onwards, it is mostly generic software. So from that, communication between these two is software to software communication. It is on more on kind of generic protocols. It can be a simple, say, Ethernet protocol, and tomorrow it could be AMQP or MQTT and all generic protocols by which the information needs to be exchanged. But then here also, one another important point I just want to underline is for that also, these protocols are, many of the protocols are not just information exchange mechanism. It is much more than that. It takes care of data modeling, and the communication happens based on model. Maybe you already know that, having asked this IEC 61850 question. You might be already aware of that kind of modeling of different IEDs and devices and all that. So here again, all those components, transformer, the boilers, furnace, or the entire power plant, the whole thing can be modeled in the system to exchange for the exchange of information. This CIM is Common Information Model. It's another IEC standard. This is also very important and interesting standard. You can model data is captured and modeled in a specific way, organized in a specific way, so that it is very easy to exchange information between two systems. So similarly here, IRM is also like that, another standard, I think interface reference model. So this kind of modeling standards also comes along with the information exchange protocol. So it's not just simple protocols, even though we say industrial protocols, it is much more than that. Again, answering to your specific question, it is the IEC 61850 is designed and framed to handle substation automation scenario effectively. It's not a generic protocol.
Thank you, sir. So I had like one more doubt. So can it be used for like you said about the interoperability? So can it be used for the base level, like integrating the PLC, DCS, and other systems to it?
Yeah, IEC 61850 cannot be used for interoperability, but for interoperability, that is the reason I just mentioned OPC publish subscriber model. So that is designed and that is being emerged for this purpose only, to meet the interchangeability, interoperability, and plug and play of devices.
Okay, thank you, sir.
Okay. Any more questions?
So my question is, we are having a subject named computational intelligence in control engineering. They will study about the fundamentals of artificial neural network and fuzzy logic.
Okay.
So can you please give some example, systems or areas that are currently working with these concepts, and also the transformation that these new trends made in the process control industry?
Okay. So say, as you wanted, I'm just picking an example of say, in a plant there are say many rotating equipments like pumps and motors and all that. So we can collect that data. Like data means traditionally in pumps and motors and all, we used to collect only the essential data, like what is the pump output pressure, and what is the input pressure, and what is the speed of the motor, those kind of the basic fundamental things. But today the scenario is different, that you will have many sensors built on top of that, the vibration, the body temperature at different places of the pump and all that. So there are many other other than the very essential traditionally collected data, we collect much more data. So all those things through the IIoT pipeline, you finally get it in a cloud. It could be a cloud or it could be on-premise. So once you have there, you keep on collecting such data. So once the pump or motor is running perfectly all right, you have the complete trend of that. You know how everything varies. And you can, with that historical data, you can have a model there, or you can, in simple words, you can say, without even going for artificial intelligence and modeling that, if there is any drastic variation in those temperature or vibration or any of those parameters, which is not a normal kind of thing, then immediately you can alarm that. But where artificial intelligence comes is, like, you capture all these data, you have huge amount of historical data, you have the real-time data coming in at the moment, and using that you can build a model by training the neural net and all that. You can have a model by referring that, you can predict that I am seeing a slight variation in, I'm just saying simple case, it may not be like that. Say that simple case could be like this: I'm seeing a slight upward variation in the vibration, and there could be a problem with the so and so part of this drive, and this may fail in next 3 months time. This is derived based on previous experience, and which is actually collected, and that knowledge is built on to the model, which is based on neural network.
Thank you, sir. Thank you for the answer.
And one another example, this is a real case also. The one I explained is also an actual case we have done. Another one is like windmill. Windmill has got say sometimes the windmill's fan blade get some cracks. So this cracks, when and how it can get cracked, even before getting the real visible crack, it can be detected by artificial intelligence. Maybe the user will be sending a drone to go and take the kind of the full picture of the whole, all the 3 blades of a windmill, and then this is analyzed by the logic built by artificial intelligence, and then we can find the anomalies or problems which are there or which may come. Even the slight variations on the data can be used to predict that. This is very popular use case. Image-based analytics and video-based analytics is a very popular use case, and in both the case, the analytics means it is actually neural net based artificial intelligence is at the back end. Just to add to that, in the first place, in many cases this kind of visual inspection happens. Every piece looked at by an expert, and say that this has got some problem is developing here, like that. And today that manual visual inspection has been removed by this. That is one part. Secondly, it's not just a visible problem. Even before the problem occurs, it can be predicted. So both are happening.
Good morning, all. Today's technical session on industrial control system today and tomorrow is a very relevant topic as far as we, the instrumentation engineers, are concerned. The session covered all important and interesting topics related with ICS, both traditional or conventional ICS and next-gen ICS in a detailed manner. We got a lot of takeaways and knowledge about the topic. No event can be successful without people who dedicate their resources and time. I must thank Mr. Manoj Vivek, GM and COE Leader, Energy and Industrial Automation, Quest Global, for finding out time to have an interaction with us. We are really happy and lucky to have you with us, sir. Hoping for more wonderful sessions like this in future as well. I thank Mr. Manoj Vivek on behalf of the department and ICONS, the Students Association of the department. I also take this opportunity to thank Placement Training and Information Bureau, NSS College of Engineering, for organizing such a wonderful session. I also thank all participants who made this session a great success. Thank you all and have a wonderful weekend. Thank you.
Thank you. Thank you all.
Thank you, Manoj, sir.
Thank you. Bye.
Yeah,
please feel free to contact if any of the topic. I may not be able to help on technical in-depth details, but I can guide you, I can direct you where and how the related information can be collected, and then what to be done. Also, I can help you on that.
Sure, sir. Sure, sir.
Okay.
Definitely. So actually, after this discussion, we identified some important topics. We have some curriculum chart and etc. So,
okay.
So during the framing of next curriculum, definitely we need your advice.
No problem. Always welcome. Anytime.
Okay, thank you.
Okay. Okay. Thank you.
So, Manoj sir, ഒരു റിക്വസ്റ്റ് കൂടെ നമ്മുടെ ഈ പ്രോജക്റ്റിനൊക്കെ കുട്ടികളെ ഹെൽപ്പ് ചെയ്യാൻ എന്തെങ്കിലും ഒരു മെന്ററിംഗ് പോലെ എന്തെങ്കിലും ഒന്ന് ഞാൻ കുട്ടികൾക്ക് എന്തെങ്കിലും വരികയാണെങ്കിൽ ഞാൻ ഒന്ന് സാറിനോട് ഹെൽപ്പ് ചോദിച്ചോട്ടെ.
Definitely. അതന്നെയാണ് ഞാൻ ഉദ്ദേശിച്ചത്. That is actually mutually beneficial. Like the topics like say OPC UA, PubSub. If we can build a skeleton, maybe multiple teams may need to work on that to give the final shape, but any incremental progress on that will be good. So we can, I can fetch, I can get the time from other experts from Quest, technical guys. They can also give you some guidance on that to define the scope and all. Yeah.
Sure, sir, sure. Thank you for sir.
Okay. Thank you very much.
Thank you.
Bye.